What's happening, everyone? Today's lesson is on sketching gradients. It's section 12.10 in the booklet and stuff. Yeah, right. This is a kind of a little kind of weird mini topic almost. That's the only question that you're going to be set today. We're going to talk through these two. So I will actually talk through that question on here as well. I just ask you to pause it and have a go at it. It's a strange little skill, this, and it basically just builds depth around what we've been doing in terms of using the gradient function to determine shapes of graphs and certain points on graphs and things like that. So what you're going to be asked here today isn't, I've never ever seen in an exam them ask you to sketch a gradient function, but it is a good idea so that you've got an idea in your head of what is going on and why certain things work. And a lot of this is going to build the basis for something that we will do next year, and we look more in depth at second order derivatives, which I think you've done already. Okay, so sketching a gradient function means that we look at what the gradient is at certain points on the graph and then try and sketch that on another graph. So don't panic about this, because I know somebody's panic about sketching graphs. All it means is it negative, is it positive, and is it high or low in terms of like, is it a big positive steep gradient, or is it a quite shallow low positive gradient? Okay, so I'm going to talk through this one here. This is your actual function, and this is your gradient function there. Okay, so the way that they've got this is they've said that the graph starts down here, and even though the graph starts in the negative part of the axis, say here, take this coordinate there, the gradient at that point, imagine being on that hill, the gradient there is really steep and it is pointing in the positive direction. Now, when we're looking at gradients, if it's going up that way, it is positive. If it's going down that way, it is negative. Okay, so at that point, and sort of for most of this section of the graph here, the gradient is really high and positive, which corresponds to this part of the graph here. It is high and positive there, isn't it? And as we move along here, if you imagine climbing it sort of around about here at this point, if you look there, our gradient there is a lot, it's still positive, it's still pointing up that way, but it's a lot shallower, which means that going from this point to this point, the gradient must have decreased, because it's gone from being really, really steep here to still being positive, but being less steep there. And that's what's happening here, isn't it? That is decreasing down to this point there. That is a stationary point. What do we know about the gradient of stationary points? We know that it is 0, which means that our gradient function graph will hit 0 at that point, which is what's going on there. And it then goes negative, doesn't it? At these points between just after the turning point, it's negative. It's pointing down that way in the negative direction. So it goes negative. And then at some point down here, it must start to become, sort of going back up. From there, it goes negative and gets more negative. So it goes lower, but then goes back up to 0 here. So between that point and that point, your gradient goes negative, keeps going negative, but then comes back up, still stays negative. It's still, see at this point here, just before the turning point, it is still negative because it would still face down that way, but then goes back up to 0. So it cuts the x-axis there, the gradient function, it will cut the x-axis again there, and it goes negative and comes back up to being negative there, to being 0 there at the turning point. And then after that, it goes negative again and gets really, really steeply negative down there, which is why that goes off down that way. Okay, so that's how you do it, and those are the things that you need to be considering. Now they've got these kind of summarized, those things that I was talking through there, they've got them kind of summarized in this little table. So at any maximum or minimum points, it means that the gradient equals 0, so it cuts the x-axis. So at that point there and at that point there, the gradient function was cut on the x-axis. Point of inflection touches the x-axis. Now, point of inflection, it depends what kind of point of inflection it is. I'd probably ignore that one for the time being. We'll talk about that maybe later on. Positive gradients means it's above the x-axis, so we had a positive gradient on our graph there, which is why it was above the x-axis there. Negative gradients, the graph sloped down for the rest of this journey there, didn't it? Which is why for the rest of it there, your gradient function is below the x-axis, it's negative. And then vertical asymptotes and horizontal asymptotes just create asymptotes themselves. You will see that in an example in a second. Okay, so let's have a go at example 19. The best way to do this, by the way, is to sketch your coordinate axes underneath the one that you've got. Okay, and then we're going to mark on certain points that are important. Okay, so we're going to mark on this point when x is -1, and we're going to mark on this point when x is 1, because those are the two turning points. Okay, that's where the gradient goes from being positive to being negative, isn't it? So they're really important because they are where it is going to cross the x-axis. So let's have a little think about what happens before this turning point. Is the gradient for this part of the graph positive or negative? Well, at any point that you pick there, your gradient is pointing up that way, isn't it? So it's positive. And it comes down to 0 there, which means that it'll be very, very steep and high there, and coming down to 0 at -1. So it's going to come down like that. Okay. Now, between this turning point and this turning point, the gradient is negative at all those points, isn't it? It starts off quite shallowly negative, but then gets quite steeply negative, and then gets shallow again back up to 0, which means it's going to curve sort of like that. And then here, the gradient is once again positive and getting steeper. So it means the gradient is positive and getting bigger going this way. So it's like that. So there is my sketch of the gradient function. So that is y equals f dash of x. Okay. Does that make sense? Well, I hope it makes sense when you can't talk to me back to the video, but hopefully that makes sense. It's a weird little thing, this, as I say. Don't panic too much if you're kind of a little bit confused about this. But basically, mark on your points where you've got turning points in the graph, and then just consider what happens in the points leading up to there, and the points between them, and the points after it. Right. Example 20 then. Exactly the same thing. We're going to sketch the gradient function for this. So where have we got a turning point on there? Oops, sorry, there we go. The only turning point we've got is there, which is at when x is -3. So let's mark that on. So we know that this thing is going to cut the x-axis. Our gradient function will hit 0 at -3. So let's consider what's happening before then. Well, up here, that gradient is now pointing down, isn't it? Which means that it must be negative, and quite steeply negative, so quite low in the negatives there, and then it's getting shallower and shallower and shallower and hits 0 there, which means that our gradient function will start off in the low negatives and come back up towards 0 at -3, 8. Okay, now let's consider what happens after this. At that point it's 0. As we move along the graph, it goes positive, doesn't it? So it starts to go into the positive bit, goes positive again up to there, quite steeply positive, but then it comes back down to be more and more and more and more shallow to this point here, the very, very end of the graph. It is almost flat again, isn't it? Okay, so we're almost hit 0. So let's just kind of sketch that. It's going to go down there like that, and then it's going to come down towards here. Now, that dashed line across there, that is an asymptote. That means that the graph does something that we call, it tends towards that line, which means the graph moves towards that line, but never touches it. Now, what that means is that the graph will never ever be perfectly parallel to that line. If it did hit that line and carried on along that line, then the gradient of it would be 0. But what it means is that it doesn't, it just goes towards 0 by tiny, tiny, tiny little steps forever, but never reaches it. You know, it's quite frustrating. So what that means is that our gradient function will tend towards 0 at that point, like that. Okay. So that's our gradient function. In part B, state the equation of the asymptote for y equals f dash of x. Well, that's when y equals 0. So the asymptote is at y equals 0. along the x-axis. Okay, so I'm going to talk you through this, and then I'm going to let you have a go on it. Okay, and then I'll sort of go through it myself, and then that's just done for this bit. So, sketch the graph of y equals f of x. To be able to sketch this graph, if we're going to be going on and doing separate graphs of f dash of x, we need to know quite a lot about this graph to be able to sketch it. So find out your roots, and your roots, remember, you can get from your diagram there, from your your equation there. Your root for this bracket gives you -1, this bracket gives you 4. That means it's going to cross the x-axis at -1, 4. You then also need to figure out what your y-intercept is going to be. Okay, and you can do that by multiplying all of this out, which is what I'd do, to be honest with you. So expand that bracket and then times it all by this bracket. Whatever is at the end, whatever number is at the end, that's where it is going to go through your y-axis. Okay, I would then you can either have a go at sketching it at that point, but to be honest with you, because you're going to be sketching your gradient functions, I think the best thing to do is probably use differentiation to figure out where your turning points are going to be. So differentiate it, set it equal to 0, and then figure out those two x values. Once you've got those two x values, that tells you your two turning points, and then you can kind of fit the shape of the graph around all of that. Okay, you're then being asked to show that f dash of x equals x minus 4 in this one. So when you differentiate f of x, you'll get a quadratic, and you just basically factorizes into this, and then use the derivative to determine the exact coordinates of the points where the gradient function cuts the coordinate axis. So once you've sketched your f dash of x, just have a little look at what it looks like and think about where that graph f dash of x cuts all the coordinate axes. So you're going to have 3 answers there. You're going to have your 2 roots for it, and you're going to have your y-intercept for it. Okay, so pause the video, have a go, and then come back and we'll go through this together. Okay, so what you should have done there was listed out your roots first. Okay, so x1 was -1 and x2 was 4. That means it cuts the x-axis at -1 and 4. Then you should have expanded it all out. And when you expand it all out, you will get x cubed minus 7x squared plus 8x plus 16. I've done that separately, by the way. I'm reading off like a little bit of notes over here. I've done it in my head. Which means that we get a y-intercept of 16. I'm going to write that up there. Okay. Now that means that I could generally sketch that if I wanted to, because it would mean that I know where it cuts these 3 things. I could kind of fit my cubic shape onto that. But because we're then going to be sketching the graph of the gradient function, I do need to know where the turning points are. So to figure out where the turning points are, I'm going to differentiate this. How do we differentiate something? Times by the power decreasing the power by 1 is what you should have all be screaming at your video screens then. So times by the power decreasing the power by 1, that's going to give me 3x squared minus 14x plus 8. Okay, now I'm just going to put that straight into my calculator. 3x squared minus 14x plus 8. Press equals, and that gives me roots there for the gradient function of 4 and 2/3. That means that they are where the stationary points are going to occur. So I can now sketch this, and I'm going to do it over this side because I'm going to draw the gradient function underneath. I'm going to mark on these important points on the x-axis. So I've got -1, I've got 2/3, and I've got 4, and I've got 16 up there somewhere. So this thing is a positive cubic, which means it's going to have that general shape. And I know that it's going to cut the x-axis at -1. It's going to top out there at 2/3, which means I have to sketch the first part of it, sort of like that. It's going to come back down there. To 4. Now when x is 4, that's a root, so we know it's going to hit 4 on the x-axis. It is also a turning point, which means it's going to bounce off the x-axis there. So it's going to come down that way to 4, and then it's going to bounce and sort of go back up that way like that. Okay, so that's the sketch of it. We're now going to sketch y equals f dash of x underneath. And we're going to mark on the points, the turning points. They're the important bits. Right, what happens before this turning point then? So down here, it's really steep, isn't it? Which means the gradient is very high and positive. And it's going to come down, come down, come down, come down, come down to hit 0 at 2/3. So it's going to go like that. Now, after 2/3, it goes negative. And it goes shallow negative, quite steeply negative, then shallow negative again, back up to 0 at 4. Like that. And then it goes positive. So there's my sketch. So that's part A, and that's part B. Okay. Right, part C, show that f dash of x equals this. Well, part C, f dash of x equals 3x squared minus 14x plus 8. It's a weird question, it's a stupid question, not to be honest with you, which will factorise into what they're asking you for there. If you wanted to, you could expand that out and see that it simplifies to that thing, but yeah, that's it basically. And then part D, use the derivative to determine the exact coordinates of the points where the gradient function, this curve, cuts the coordinate axis. Well, we know 2 of them already. We know that it cuts there and there, and that coordinate is 2/3, 0, and this coordinate is 4, 0. What is the other point where it cuts the coordinate axis? Well, it cuts it there, doesn't it? Which means that that is the y-intercept of this, which means it's going to cut it there, which means that your third point is 0, 8, and that's it. Okay, so as I say, a little kind of strange, almost kind of just enrichment thing there for the time being. Okay, just looking at gradient functions and their graphs. Do not panic too much if that didn't make an awful lot of sense. It's important to have an understanding of what's going on here, but it's something that is a building block for something else. And I think when you come to do second order derivatives, especially next year, I'm doing them here 13s at the minute, the idea of knowing when gradients change from positive to negative and what effect that has on the graphs of the gradients is a good basis for then coming on to look at what we do in terms of something called concavity and convexity. Okay, so good luck with that, and any issues, let me know.